Imagine that you're trying to predict the price of a house based on its features. In general, you know that with an increase in house size, the price of the house also increases. You have a set of data points, you decide to plot them on a graph, and visualize the relationship between these two measures. And eventually, you want to find out the price of a 1600 square foot house. It turns out that this house would cost you about 520,000 US dollars. So, how do you come to this conclusion? And what is this problem? Well, this is linear regression. And let's check it out visually how this model actually works. Linear regression is a part of techniques called supervised learning, where the output that we desire is known or labeled. In our case, it was the price of the house. And regression tells us that the output would also be continuous rather than categorical. In this model, we try to fit a line, and let's see how we come to this conclusion. Well, we try to minimize something called the cost function. The cost function is essentially a metric to evaluate how well our predictor is performing. On the left, you can see the line on the red, which is our prediction, and the yellow dots, which are the actual price. In mean squared error, you just take the difference between the prediction and the actual value. You square those values, sum them up, and you take an average over the entire samples. This gives you a single number that gives you an evaluation of how well your model is performing. So, in essence, MSE measures the average squared difference between predicted and actual values. Now, you might be wondering why squared and why not directly the residual values? Well, intuitively, you can see that if there's a positive value and a negative value in the residual, they might cancel each other out, rendering them useless for the prediction's cost. So you just take the square, that gets rid of the sign, and that fixes the problem essentially about the positive and negative residuals. So to just summarize the process of the mathematical formulation of linear regression, we started off with a basic linear regression equation, y is equal to mx plus c. We typically don't write it like this. We use the vector notation, which is really handy, makes life a lot easier. And then we have a cost function, which gives us a measure of performance. We want to minimize this. To minimize this, we calculate the gradient of the cost function, set that gradient equal to 0, and we try to find theta. And that gives us an analytical solution to the problem. We typically don't use this analytical solution though, and the reason for that is outside the scope of this video, but to give you a hint, it has to do with something about the invertibility of the matrix X transpose X. You can look more into this later on your own. So what do we use instead? Well, we use an iterative method called gradient descent. You can imagine it as taking small steps towards the minimum of the function rather than calculating the minimum directly. With each iteration, you calculate the gradient and you try to move towards the negative of the gradient, which will get you the minimum point of the function itself. As you can see, which with each iteration, we have a lower and lower cost. Eventually, there comes a point where the cost doesn't change, and that is the point of convergence. Putting this all together with linear regression, let's see a visual of how our linear model would change based on gradient descent. We start off with a few points and a line that's not really fit to the data at all. It has a very high cost, but with each iteration, we change our M and B, which are the parameters of our model, and it moves closer and closer to those points, reducing the cost. Eventually, we've come to a conclusion where the cost isn't changing that much. So taking more iterations really isn't that useful. And here's the solution to our problem. We now say that our line is fit.